This tutorial is entitled Waveform Measurements. Utilizing a AC circuit with the very simple structure that has been used in other tutorials, we will illustrate how to make various waveform measurements, in some sense very similar to that would be done on an oscilloscope. Now, this basic RC circuit is the same that was considered in several modules, although the capacitor value has been changed. To make the display look a little better for this particular tutorial, I have redesigned the circuit to have a 3 dB frequency at 1 kilohertz. The original circuit had a time constant of 1K times 10 to the minus 6, which was 10 to the minus 3, or 1 millisecond. If one calculates the 3 dB frequency based on that, you get 159.2 hertz approximately. But I've redesigned it to have a 1 kilohertz 3 dB frequency. It's not a very sharp type of cutoff, but at least it gives us a sense of what we can make a measurement with. And the frequency here is at 1 kilohertz with a peak value of 1 volt and 0 degrees phase angle. So let's do a transient analysis on this. I'm going to click up here on the grapher and go down to transient analysis. Now, because the time constant is 0.159 milliseconds, 5 time constants is less than 1 millisecond. However, there's nothing wrong with going to a time greater than 5 time constants to make a measurement. And in order to make it occur right at the beginning of a cycle, I've set it on 1 millisecond, which is more than 5 time constant. So the circuit should be fully settled by the time that we display the output. And I'm running it initially over 2 cycles, so it's running from 1 to 3, so we can take at least initial view of the output signal. The time step is actually down at 1 microsecond, which should give it very good accuracy. And we set the initial condition to 0, meaning the capacitor voltage is starting out with 0 voltage. Let's check the quantities for the output. I've already put in V in and V out, the input voltage and the output voltage. So let's click Simulate. Well, as you see, you have 2 cycles of the input and 2 cycles of the output, but there is a phase lag in the output. The output is down in peak value, as you would expect. The voltage on the capacitor at the 3 dB, which is really 3.01 dB down. It's around 0.707 as we would expect, but we'll get around to measuring that shortly. Now, we can make measurements on the signal as it is, but we can get even better measurements if we change the scale so we only have 1 cycle, and then perhaps even a half cycle would do even better. But let's just go back and click on the transient again. I guess I need to get out of here first and then go back to transient. And this time I'm going to just go from 1 millisecond to 2 milliseconds. So I'm changing the time scale such that I have just 1 cycle, and hit Simulate, and we have 1 cycle with the 1 volt input and the output, which at that particular frequency will be about 0.707 volts. Well, anyway, the cursor option has already been set, so we have 2 cursors here, and you can make various measurements by just moving the cursors along. This is cursor 1 and cursor 2, and indeed, for many purposes, you can just move these along and read X1 and Y1 for cursor 1 and X2 and Y2 for cursor 2, but I'm going to show some different kinds of measurements here, some that can get a little more accuracy in the process. And I think I'm going to use cursor 1 for that purpose, just as a matter of reference. So let me drag cursor 1 over to the right here and click on it so it's been selected. Okay, this curve, the triangles on it mean it's been selected. So if I want to make a peak value measurement, you can move this along to the peak, but let's let Multisim do that for us. click up here on cursor, and it says go to next Y max. So I'm going to click on that, and notice what happened. The cursor moved over and reached the maximum value of waveform 1. Well, of course, we can read it at 1 volt, but let's look down here at X1 and Y1. X1 occurs at 1.25 milliseconds, and Y1 occurs at with a value of 999.9996. That's about as close to 1 as you can get. Because there are non-zero step sizes in the approximation, what's being done internally is a numerical solution to a differential equation has been done, and so you don't get absolute correctness, but you can't measure those things anyway in a real circuit that accurately, so that's for all practical purposes 1. Now let's take the same cursor. Since we've got it out, we could use the other one if need to be, but it's probably easier to use this one. Before I do that, though, let's note that that occurs for 1.25 milliseconds. That's kind of interesting to note because that's 1/4 of a cycle, and we'll come back to that for a frequency kind of measurement. As a matter of fact, since this is determining the maximum value, that is 1/4 cycle at the frequency. So if we have 1.25 milliseconds based on this particular thing, this means that 1 cycle would be 4 times that, since we started at 1, remember, so it's really only 0.25 after the start, so 4 times that would be 1 millisecond, giving us a frequency of 1 kilohertz. So that's one way to actually estimate it even at this point, or to make a measurement. But now let's see if we can't go to the select the second waveform and make sure I still have that one selected. Now what I'm going to do is have it determine the maximum of this waveform. So I'll go back to cursor and set the next Y max, and it moves over, and now the Y value, if you look down here, is there's a little m at the end, so it's 0.707, and that is the voltage expected across the capacitor at the 3 dB down frequency based on 1 volt at the input. Now let's talk about the phase shift measurements. I'll go ahead and use this particular display. To get even better accuracy, we could actually show this only over a quarter cycle and do even better, but I think this will be good enough for the purpose intended. Now what we need to do, I think I'm going to move, well, cursor 1 is already set at the beginning point, so what I want to do is to find a 0. Now I'm moving this back to the left of the 0 crossing to make a point. Let's go back to cursor, and you have 2 situations here in order to set the Y value at whatever you want it to be. Now this one moves the cursor to the right, to the next point on the right at which the value is what you specify, and this one sets it on the left. Now I'm to the left of that 0 crossing, so I want to use the first one here, and it says go to set Y value equal, and I'll put 0 in that slot and hit OK, and notice that moved to 0. Now if you were making a time measurement between 2 different points, you could actually go back and use the other cursor to determine one of those points. But I know that this one is already set at 0 time relative to the time scale. It's really starting at 1 millisecond, but it's our 0 reference is at 1 millisecond. Now let me illustrate, though, another thing. That is, if I move this over to the right, and I see I want to move it back to that 0 crossing, I use the same cursor idea again, but this time I'll use the second set Y value, and again set it equal to 0, and click on OK, and it moved to the left. and it came back to the very same point. Now, once again, because of the fact that I have a V out at 1.125 for all practical purposes, it is 0.125 past 0, so that means that we're measuring the time difference of 0.125. However, if you look down at dx, dx is the difference between the corresponding values of time, and that is the 0.125 milliseconds or 125 microseconds. So once again, that's 1/4 of one cycle, and 1/4 of one cycle, if you do a ratio and proportion here, the period is actually 1 millisecond. Now, 0.125 millisecond is 1/8 of one cycle. So in terms of phase angle, it is 1/8 of 360 degrees, 1/8 of 360 degrees, which turns out to be 45 degrees. And that's what we expect at the 3 dB frequency. So we have measured the phase. So using these utilities, you can determine various parameters of waveforms, determine time shifts, phase angles, peak values, and so forth. Now, these utilities that I just used give you some advantage in getting an accurate measurement without having to hone in exactly on the points. But of course, you can still, for many cases, you can just move the cursors around until you get to the right value. So this concludes this particular presentation.